Welcome to This Explainer. We hear about artificial intelligence literally every single day. And usually we talk about it like it was just this convenient leap in tech, right? Like some cool new tool we just decided to build because we could. But what if I told you that's totally backward? What if AI wasn't a choice at all, but a strict mathematical and computational necessity? Picture this, a fast-moving montage right in front of your eyes. 3 billion biological sequences. A, T, C, G, just scrolling relentlessly, faster and faster. It's this overwhelming tidal wave of genetic data that your eyes can barely even track, let alone actually comprehend. Boom. Now the scene instantly jumps to a wildly complex flight dashboard. You're at exactly 3,200 feet in the air. You've got flashing alerts, alarming descent rates, and just a total barrage of variables screaming for your attention in the middle of a high-stakes, life-or-death crisis. Now throw in flashing transaction alerts. We're talking 100,000 unanchored, chaotic data components completely flooding the screen. Imagine a human silhouette just totally drowning in this sheer volume of data, completely unable to process it all. But then, watch. The chaos suddenly reorganizes. The noise just fades away. Beautiful patterns emerge right out of the static, forming this clean, automated digital stream, entirely controlled by artificial intelligence. It's a pretty powerful image, right? So we really need to pause right here and ask ourselves a totally fundamental question. Why did AI absolutely have to be invented? Why did our traditional, rigid, classical programming just fundamentally break down the second it faced the chaotic complexity of the real world? Let's dive into Section 1, the limits of logic. To really get why we needed a complete revolution, we first got to define what classical programming actually is. Look, if you're doing something low-dimensional and super predictable, say calculating a tax return or figuring out simple bank interest, classical programming is absolutely perfect for the job. It's built on rigid, top-down, explicit rules that a human coder manually types out. But here's the catch. The real world just doesn't operate on simple if this then that logic, and this is exactly why machine learning was necessary. Instead of sitting around waiting for a human to write out a million rigid rules, it works from the bottom up. It actively seeks out patterns in massive oceans of data, adapts on the fly, and calculates probabilities. Moving right along to Section 2, solving the DNA puzzle. Let's step into our very first real-world case study to see exactly where classical logic hit a massive, immovable brick wall. I'm talking about the Human Genome Project. Imagine trying to assemble a gigantic jigsaw puzzle made of 3 billion pieces. But you're using classical algorithms that only know how to look for exact, predefined matches. The public consortium, well, they played it incredibly safe. They used a hierarchical shotgun method, basically mapping small, known sections really slowly to minimize any risk. But then you had a private company, Celera Genomics, and they took a massive swing. They went with the whole genome shotgun approach. They sheared the entire genome into millions of completely unmapped fragments, basically crossing their fingers and hoping that sheer classical computational power could just stitch the whole puzzle back together all at once. But Celera hit a massive structural barrier. You see, over 50% of the human genome is actually made of identical repeating DNA sequences. So those classical greedy algorithms, the ones programmed to just rigidly grab the most immediate, obvious match, they were completely tricked. Because the sequences looked exactly identical, the rules-based software actually collapsed distant, completely different regions of the genome into a single piece. This computational failure is what we call a compression/expansion misassembly, and it left them with over 100,000 unanchored components. Classical if-then rules literally just could not overcome the repeating structure of human DNA. Let's transition over to Section 3, Flight 1549 Rigid Rules. We're going to look at a completely different environment where deterministic logic utterly collapsed. And this time, we aren't talking about microscopic DNA. We're talking about a high-stakes aviation emergency. Picture this. January 15th, 2009. U.S. Airways Flight 1549 strikes a massive flock of migratory Canada geese just 2 minutes after taking off from LaGuardia. At an altitude of only 3,200 feet, this bird strike completely destroys the core of both engines. Suddenly, Captain Chesley Sullenberger and First Officer Jeffrey Skiles are thrust into a chaotic, terrifying situation that their pre-programmed rules simply were not designed to handle. We all know the incredible result, right? The miracle on the Hudson. An Airbus A320 safely ditched right in the frigid river, passengers standing out on the wings waiting for rescue.
But looking at this outcome forces us to ask a really critical, systemic question. Why did the plane's highly detailed emergency manual, literally the ultimate set of rigid aviation rules, completely fail to prevent this, or even properly guide the crew through it?
Here is the wild truth. That rigid rulebook actually induced dangerous task saturation. The Quick Reference Handbook tech list completely failed them, and for three huge reasons. First off, it was designed with the hard assumption that a dual-engine failure would only ever happen above 20,000 feet, which would theoretically give the crew plenty of time. Second, the rigid step-by-step logic basically forced the first officer to waste 30 to 40 critical seconds trying to relight engines that were physically shattered. And finally, the absolutely crucial steps for water ditching, they were buried way at the very end of a 3-page list. It was pure human adaptability and heuristics, not some deterministic high-altitude checklist that saved those lives.
Which brings us to Section 4, the curse of dimensionality.
Okay, so let's slow down for a second. What actually connects the failure of those DNA sequencing algorithms and the failure of that rigid aviation checklist? Well, it's a profound mathematical culprit. Take a look at this incredibly tiny percentage, 0.00027%. This represents what we call the empty space phenomenon. To put that into perspective, think of a massive multi-dimensional room. As you add more and more variables or dimensions, almost all of the volume pushes out into the far corners. The center becomes completely, utterly empty. So your data isn't clustered together neatly anymore. It is literally drowning in this vast empty space. Now, in classical programming, we rely heavily on rules based on distance to group similar things together. But as your variables scale up into the thousands, we hit something called distance metrics collapse. In these massive, high-dimensional spaces, the mathematical difference between the absolute nearest data point and the farthest data point effectively shrinks to zero. Just imagine standing in a pitch-black void where every single object around you looks like it's the exact same distance away. You obviously can't write a simple if-then rule to navigate that, because traditional distance-based logic completely and totally breaks down.
And this perfectly sets up Section 5, the probabilistic AI solution.
This massive mathematical roadblock is exactly why artificial intelligence was an absolute necessity. We literally had to conquer the curse of dimensionality. Classical decision trees, they use this rigid trial-and-error approach. They just jump around blindly, which fails instantly the second you put them in massive, empty dimensional spaces. But modern AI, it uses differentiable neural networks. Instead of jumping rigidly from point to point, it flows. Using something called gradient optimization, AI smoothly navigates these massive, unstructured spaces, almost like a ball rolling down a bumpy hill, to naturally find the lowest point. It learns the terrain automatically, propagating errors backward to adjust itself continuously, instead of constantly demanding a rigid, pre-written map.
So the absolutely crucial point we need to walk away with today is this. Artificial intelligence had to be invented, simply because the real world is far too complex, way too dimensional, and vastly too unpredictable for static if-then rules. But as we fully embrace this incredible shift from deterministic logic to probabilistic systems, it really makes you wonder, are we truly ready to hand over our most critical, high-stakes decisions to systems that learn, rather than strictly following our rules? It's a massive shift in how we interact with the world. Thank you so much for joining me on this explainer. I hope it sparked some real curiosity, and I will see you next time.